The other big place that we find linear models is when we're mixing things and we know how we want the final mixture to turn out. So I'm just going to give you an example of a mixture. Suppose we have an $8,000 budget to buy tables and chairs for a classroom. Tables cost $250 and chairs cost $75. We're going to write an equation relating T, the number of tables we buy, to C, the number of chairs we buy. Right. Now, just thinking about this with common sense, right, it's pretty clear that the total amount that we spend is going to be the amount we spend on tables plus the amount we spend on chairs. Now, the total amount we spend, we want that to be $8,000. How much do we spend on tables? Well, if we buy T tables, and each one costs $250, what will that cost? The amount each table costs times the number of tables. So 250 times T. And how much will we spend on chairs? Well, again, the amount each chair costs times the number of chairs. And there's our linear equation. Our total budget equals the amount we spent on tables plus the amount we spent on chairs. And this is the general form when we're writing a linear equation to describe a mixture. Total amount equals amount from the first part of the mixture plus amount from the second part of the mixture. Right, here's another example that looks very different. Suppose we're considering two investments, A and B. A returns 6% interest. That means the interest from A each year will be 6% of the amount that we invest in A. B returns 8% interest. That means the amount of interest we get from B each year will be 8% of the amount we invest in B. We want a $900 return on our investment. Write an equation relating the amount we invest in A to the amount we invest in B. This one seems a little bit more complicated than the tables and chairs story for some reason. Maybe because this is less immediately familiar, maybe because the percents throw us off a little bit. It's very often helpful when considering mixtures to organize our information into a table. And the kind of tables that we use for organizing information about mixtures look something like this. We have a row for each of the parts, and we have a row for the mixture. I think it's important to label these because this is a device for organizing our thoughts. We want all of our thoughts written down on the piece of paper. I like to put a line between the two parts and the mixture also, because it helps me see what I'm doing. Let's see. The amount we invest in A is A, the amount we invest in B is B. The interest we earn on the mixture we want to have be $900. Well, the interest that we earn on the mixture will be the interest that we earn on the first investment plus the interest we earn on the second investment, right? A returns 6%. What's 6% of A? That's just 0.06 times A. Remember, to write a percent as a decimal, we just divide it by 100. How much interest do we get on B? Just the same, 0.08 B. So what will our equation be? The interest from the first thing plus the interest from the second thing equals the total interest. Mixtures can get even a little bit more complicated than this. Let's see one more. Suppose we work at a compounding pharmacy and we want to mix two solutions. A, which contains 7% sodium benzoate, and B, which contains 20% sodium benzoate, to create a mixture which contains 14% sodium benzoate. We would like to write a linear equation relating the amount of solution A we use to the amount of solution B we use. Again, this is kind of complicated, so I'm going to organize the information in a table. And, you know, there's a lot of stuff about percents in here that I want to make sure I'm keeping straight. So I'm going to make a column for percents as well. So A and B, are the amounts of solution A and solution B. Solution A contains 7% sodium benzoate. Solution B contains 20% sodium benzoate. And we want the mixture to contain 14% sodium benzoate. Notice something about this column. It doesn't make sense to add percentages here, right? Because this is 7% of A, 20% of B. These are percentages with different bases, so it doesn't make sense to add them. If I mix 100% juice with 100% juice, I don't get something that's 200% juice. What it does make sense to do, though, right, just like we did before, is put together the amounts of sodium benzoate. This will be 7% of A. This will be 20% of B. This will be 14% of what? Well, it'll be 14% of the full mixture, right? If I mix A units of solution A with B units of solution B, how much have I got in the mixture? That's right, A plus B. So the amount of sodium benzoate in the mixture will be 14% of A plus B. What equation does that give us? Well, the amount from A plus the amount from B equals the amount in the mixture. Parentheses. Is this still a linear equation? Well, yeah, we still aren't taking any powers of variables. We still aren't multiplying any variables by each other. Okay, I'm going to ask you to come up with one of these equations just to try this. Suppose that Alice makes $15 per hour as a tutor and $8.75 per hour as a cashier. If she must make $200 per week, write a linear equation relating the number of hours she tutors in a given week and the number of hours she works as a cashier. Pause the video and try this now. Now again, this one is a little bit more straightforward, but I am going to organize the information in a table just for the practice. So our two components are working as a tutor, working as a cashier, and the two together. The hours are T and C, and then we have information about her hourly rates. Right, she makes $15 per hour as a tutor and $8.75 as a cashier. We could leave this column out if we liked, because what we're really interested in is how much money she earns. If she works T hours for $15 per hour as a tutor, she earns 15 T dollars. If she works C hours for $8.75 per hour as a cashier, she makes 8.75 C dollars. And we want the amount she earns to add up to $200. So again, the earnings from the two components add together to give the total earnings. The amount she earns as a tutor plus the amount she earns as a cashier adds up to $200.